Okay, so RAM. So let's pretend that to visualize these chips, just say that they are like columns of, and each row is a byte, right? So each one of these has like huge columns, and each row is a byte, and a byte has an address, just like in Excel, right? A row has a number. And of course, since this chip is one gig, that means it has 1 billion bytes, 1 billion addresses. It's like imagine like a huge Excel file that has 1 billion rows. So when your computer starts, so you have your applications on your hard drive and they're sitting there. When you start your computer, your operating system gets loaded. So in some parts of these bytes, your operating system gets from the out from the hard drive onto the RAM, and it occupies these on the RAM, right? Most likely, the operating system occupies the first addressable bytes. So your kernel, everything goes from like 0 all the way down to whatever, however big your operating system is. Let's just make it in red, right? So here you have your operating system. When you start Microsoft Paint or whatever, your operating system just says, all right, Paint is going to go from here to here, and it loads the code for Paint, and it loads the code for this program, and then your program, once you run it, when you click Start, your operating system is going to do the same thing it does to the other program. It's going to find like a free spot somewhere, and it's going to say, all right, everything in this green area is going to be your actual code. You can pretty much take each one of these lines, a gross exaggeration, right? This is a gross exaggeration, but basically it allocates some bytes and it pretty much writes down, copy like the exact, these turn into commands, and they hold a certain spot, a certain space here. Within this allocated space, these lines will occupy, let's say, this much, and we'll color it in like a darker green. The rest is free. The rest is whatever you enter between these two brackets. See the main? The main is what runs. By just doing x equals 8, meaning 8 goes to x, what the program is going to do is it's going to find one of these guys. Well, right now they're all green. They're free. It's going to take a random one. Let's pretend it's going to take this one, and somehow in there it's going to say that its tag is x, and the value that it holds is 8. Let's see if I can zoom in some more and make it black. So it knows that at address 245 there's something called x, and it holds 8. Okay, that's still a gross exaggeration because 8 is written in binary, and an integer is 2 bytes. So it's actually this and that, 2 bytes it's going to take. And now we're going to look at what it actually looks like. 8 in binary is 1, 0, 0, 0. So it's going to fill everything with zeros. Right? I'm not sure if this is going to actually show. And then 1, 0, 0, 0. Whoops, I skipped 1. So this is what it's going to look like in RAM, somewhere in RAM. Oh, this is terrible. Definitely can't see the color. Missed a 0 here. This is a 1. I wonder if I can bold it. Right. So this is basically the equivalent of this line, along with the x. It's an extra. Let's just pretend that there's a tag stuck onto it. You don't. I'll explain later, but that's basically what's happening. If I were to do, like I explained to you the other time, another int y is now equals to, like, say 3. Somewhere in memory, like when this program starts, it's gonna read this line and allocate x here. It's going to read this line, and it's going to find it almost looks random, but it finds like a, because once you look at memories of, it's not automatically the next one in line, is what I'm trying to say here. It's going to put a y here, and 3 in binary is like 1001. No, sorry, that's 4. 1, 1. And the rest is all zeros, and I don't know why. I'm just going to do that in order really, really fast. Right, this is what it's going to look like. And now if we do a character C is equal to this character, let's say capital A. What it does is going to be continued in the next video.